welcome everyone to the second lecture. So there was a bit of drama, which is still ongoing, which is that, which is that my Apple Pencil got discharged, and therefore I have to write at least for the next few minutes with my finger, or with I have a stylus, but it's not really working. Let's see if I can use it. Yeah, it's doing some weird things. Let's see. Okay, fine. I think my finger works better than the stylus actually. So good. So you'll have to tolerate that I'm going to write very big and very ugly for some time. Good. So let's remind ourselves what we did last time. We basically did two things. On one side, we considered some properties of the real line R. And out of those properties, we abstracted a few, which we call topological. And the properties that we call topological are basically the open sets in R. And if you remember what these are that if X is in some subset X, then X should be inside an open interval which is fully contained in that set X. So every time there's a point in R which is in some set X, then it should be true that X is contained in an open interval which is fully contained in that set X. Then the set capital X is called an open set in R. Okay. Then we wrote some properties of this, and with those properties, we gave a completely abstract definition which does not talk about intervals and does not talk about R at all. Okay. In this one, we take the so this is topological space. So here we take any set S and a set U, which is a collection of subsets. So U is a collection of subsets of S. And it's any collection I want, but it has to satisfy certain axioms. And I wrote those last time. And satisfying the axioms I wrote last time. I hope you have your own notes or the book with you. And the axioms you can sort of think of as, somehow I don't have the page advance. Sorry, this is really not going well. Yeah. So satisfying axioms 1, 2, and 3, which I wrote last time. And with that, this structure is a topological space. So one was that phi and S are in the collection U. 2 was that arbitrary unions of elements of U are again in U, of Ui in U are again in U. And 3, sorry for this, was that finite intersections of elements of Ui are again in U. So those were the axioms. I gave some examples involving very abstract sets. And there are a couple more examples I'd like to give you right now, and then we'll move on to define more properties of topological spaces, and eventually attack the issue which I flagged last time as the key motivating issue, which is how are we going to define the notion of continuity? Okay. So the examples I want to give some what are sometimes called trivial examples. They are trivial because they are extreme. You can think of them as extreme. So I told you that we need a set S and a collection U. So one example which I can define for any set S is that U contains only the empty set and the full set S, nothing else. So it's a topology in which there aren't many open sets. The only open sets are the empty set and the full set. It's easy to verify that this satisfies all the axioms. So this is a topological space, and it's well defined on all sets S. And it goes by the name, which I think is meant to be slightly humorous, of indiscrete topology. Sounds a bit like a pun. Indiscrete with a different spelling has a different meaning, but anyway, this is what it's called. Now, there's another extreme example, which is U equals power set of S, that is all subsets of S. It's the collection of all subsets. Okay, so in the first example, we have no open sets except phi and S, which have to be always there. While in the second example, every subset is there in the collection of open sets. And this is called the discrete topology. Now, these are important points of reference because they show us, they give us examples which we can apply to pretty much anything. So, whenever anybody gets this in their head that there's only one possible topology on my space, you can always tell them, no, try the discrete topology. For example, on R, where we discussed a usual topology, we can also define the indiscrete and the discrete topology. And with those topologies, R is a very different looking space with the same points, exactly the same points, X, any real number X, but what we call open sets are now going to be totally different. So that's a kind of a fun thing, but it also is somewhat illuminating. Okay, now let's move on to a few new definitions, and I want to start with the concept of a metric space. So note that in principle, my topological space, which may be made up of a lamp, a desk, and a laptop, has no concept of distance. What's the distance between two objects? Well, it's up to us to define what that means. So in general, a topological space doesn't have a distance concept at all, and it's not a metric space. But I can define something called a metric space on any set, not even a topological space, and then I can apply that to a topological space. Okay, so metric is a very beautiful idea because it can be assigned. It's a concept which is somewhat like distance, but can be assigned to any space S. So when I just say S, it's clear that I don't have any topology in mind. When I put S comma U, then that U is the topology on the set S. So right now the set is S, and it's S along with a map. So it's S with a map that takes any pair of points, X and Y, both of which are in S, and assigns a positive, non-negative rather, real number D, which is in R plus. R plus is the set of real numbers starting from 0 and going up to infinity. Okay, but in order to be a metric space, so this D of xy will be called in words the distance between the points X and Y. But to be a metric space, it has to again satisfy three axioms. So this is always how mathematical definitions are given, that you define some structure and then it's a valid structure if it satisfies certain axioms. First axiom is that D of 2 points X and Y will be 0 if and only if X and Y are the same point. So the only pair of points which have 0 distance between them must be the same point. Any two distinct points should not have that property. Now, all of you are physicists and you're probably thinking, in Minkowski space, we know that we have some kind of Minkowski metric. It's already dead. It didn't satisfy axiom 1 because points which are like separated have dxy equals 0, but x is not y. This is supposed to be if and only if. So technically, Minkowski space time or any space time with different signature for time and space isn't a metric space. In fact, it's something a little different. It's called a pseudo-Riemannian rather than a Riemannian space when it's a manifold. So we'll come to it a bit late in the course. For now, the axioms are going to describe more familiar metrics which are there on spaces, not space-times. Okay. Now, the distance between 2 points is very obviously symmetric under exchange of the points. So that's needed. D of xy is the same as d of y and x. And the third one is a very famous inequality called the triangle inequality, which says that the sum of two sides of a triangle is more than the length of the third side. Any two sides, if you add up the lengths, is the same, is greater than or equal to the length of the third. So with these three axioms, the map D, which takes me from the Cartesian product of S with itself. Cartesian product just means that I pick two elements of S rather than one element of S. So one belongs to this S, one belongs to the next S, and those are X and Y, and it maps them to R plus is called a metric on S. So I emphasize this didn't have anything to do with topology. We didn't assume a topological space. However, we can apply this to a topological space and we find it's very useful. Okay, first let me give you a few examples of metrics. It's always good to have some examples to fix our ideas. So one of them is on R. I can define d of xy to be mod of x minus y. Note the mod is essential, because otherwise x minus y is not symmetric under interchange, but with the mod it is, and it satisfies the other two properties manifestly. Similarly, on R, any Euclidean space R to the n, for example, R to the 2 is the plane, R to the 3 is the 3 volume. On any of those, I can just generalize this by saying that I can label the points by vectors x and y or by their coordinates, and I'll just take the distance function to be mod of x minus y. But again, these are only examples. Again, on R, I could invent some completely weird metric if I wanted. Then it would be a new metric on R. I can do that on any space. There's nothing like a unique metric on a given space. There's an interesting exercise. Does on R, so does d of xy equal x minus y whole squared define a metric on R? So not mod of x minus y, but actually the square of x minus y. Just a new, looks like a new metric. You have to check all the axioms and see whether it really is a metric or not. Now, these were just examples of metrics. There are also weird metrics. So let me give you an example, another example of a weird metric. This can be defined on any space. D of x and y is equal to 0 if x equals y. This obviously we have to say because it's part of the axioms. But we'll say that d of x and y is 1 if x is not equal to y. So this is a very cool kind of metric. It just says that between any pair of objects, the distance is 1. Unless they are the same object, then the distance is 0. This is actually a metric, can be defined on any space. So again, it's a little trivial kind of thing, but it's interesting to, I don't know if it has a name, but it's interesting to check. This particular one, in fact, you have to check that it is a metric. This is a genuine, valid metric. So I guess that's a hint. The previous one, x minus y squared, isn't a valid metric, doesn't satisfy the axioms. Okay. So why did we discuss metrics on topological space? Why did we discuss metrics in a course on topology at all? And the answer is that metric can be used to define a topology. So not so bad, writing with my finger. I'm getting good at this. Okay. So how are we going to do it? We are going to say the following. First of all, we are going to define a concept, an abstract concept called open disk. Now, there's also a concrete concept called open disk on R2 on the plane. We know what a disk looks like. And this is the abstract version of it, which would apply to all metric spaces, not just to R2. So you have to always make that change in your mind between the concrete example based around Euclidean space and the abstract example, which can be on any space. So we'll define it as the following: that if given a set S uh, for x in the set X S, the disk dxa is called the open disk with radius a. So a is a real number greater than 0. So a is greater than 0. It's a real number. X, on the other hand, is an abstract point in S. So this is defined to be the set of all points in S such that the distance of that point from X is strictly less than the real number a. Remember, distance was a real number, so I can compare it with the number a. So basically, the open disk is all points closer than the value a to the given original point. So the disk is based at x. X is like the central point, if you like, and it contains all the other points in S, which are that distance or less from a. Now, obviously, in R2, this is exactly the usual disk. But we can do this with any dxy, which is a valid metric, and there can be very weird metrics. Okay, good. Now, this is the first step to defining a topology using a metric. And the second step is to say that any set X, which is a subset of S, is an open set if small x being a point in that set implies that small x is contained in an open disk around itself, which is fully contained in the subset X. Now, where have you seen this before? Well, this is how we defined open set on R in terms of open intervals. We said that something in R is an open set in the usual topology if a point in that subset can be enclosed in an open interval which fully lies inside the subset. And now we've simply replaced open interval by abstract open disk in a metric space. Of course, the open interval is a concrete example of an open disk in a metric space on R. Okay, but this relies on any metric that I might choose to define, small d of x and y. Okay, now the point is that I've now said how to categorize any subset of any set S. Okay, I'll just call it an open set. I'll just name it an open set if it satisfies the property that I can fit an open disk in it, whatever the open disk might be in that metric space. Okay, and now it's an exercise to check that this satisfies the axioms of a topological space. I haven't shown that it does, but instead I've sort of defined it in an easy way. I've defined the topological space by its open disks through a metric, and I claim that it's a topological space. Therefore, first of all, empty set and full set should be in the collection of subsets. Secondly, the union of any number of subsets of open sets should be open. And thirdly, the intersection of finitely many subsets should also be open. Okay, so that's something to check. Good. So, for example, now you could ask, this is another exercise, it's all given in the book. Supposing I consider that weird metric I defined a few minutes ago, dxy equals 0 for x equals y and equals 1 for x not equal to y. What are the open disks and what does the topology look like? what is the corresponding topology. Okay, little bit of notation here. A topology or a topological space defined using this procedure, namely start with a metric dxy, small dxy, then define open disks capital D, and then write this definition of open sets. This thing was called a metric topology. It's a sort of obvious notation. Metric topology is the topology defined on a set using a metric. And it's an option. You can have a metric topology. You may have a topology that doesn't come from a metric, but it's a convenience. Okay. And I hope I've emphasized enough that metric can be defined on any set. A topology can be defined on any set. That's the collection of its open sets. And metric topology is when I use the metric to define the topology. Good. Okay, now I'll say one more or two more words and then look in the chat box. But my impression is the chat box is empty. I think we have just frightened all of you from asking questions. And that I think has gone a little bit to the other extreme. So, I'm closing the chat box, but I think you should write your questions in the chat box even now. And I'll look at it when I finish this next section, which I'm turning to. Now,
So the chat is disabled.
disabled.
Oh, right. It's open now. It's open now.
Open. Okay, good, good. Okay, sorry, that was not planned actually. Chat wasn't to be disabled.
Sorry, I thought that you asked me to disable the chat.
No, actually, I didn't. I just said that I won't look at it.
Okay, okay.
It's a little bit of what is called discipline on my part, which I don't keep very well. But a few students and also a few colleagues advised me to keep this discipline, so I'm doing that. So you can type all your questions. I'll just check them when I feel like, which is after another 3 minutes or so. Good. Okay, so with metric, we saw that metric can give a basis for a metric can give a topology called the metric topology. And now we'll come to an sort of slightly related but not completely the same concept, basis for a topology. Now, what's a basis? Well, here the problem is as follows. If you remember last time, I considered a set with 3 elements and I gave an example of a topology on that, which is a set of open sets. But if your topology has infinitely many open sets in it, how on earth are you going to list it? You can't possibly keep writing all the elements of capital U. Okay, it's a pain and it's also not desirable. That's not how mathematics is done. We would like to have some declaration which will tell us right away what are the open sets in that topology. So for that, we can use some properties which are true in R. Again, we can use motivation from the real line and we'll take them to our abstract space. Notice that recall that in R, recall that in R, we had open intervals A comma B and we had open sets. These were not the same, and last time a lot of people had fun getting confused because they weren't listening to the words carefully. Open interval is literally A less than X less than B. And open sets was that X is capital X is an open set if X in X implies X in AB fully contained in X. These were 2 different things, but it was open sets which was the whole thing. The whole topology was open sets, but somehow open intervals seem to be enough information. If you understand open intervals, even though they are not all the open sets, you can make all the open sets from them. That's the idea of basis. Basis is always something small from which you can make everything you need. Okay, so good. Now, what are the properties of open intervals? Let's list some properties. And then it'll turn out these are the properties we need to copy for a general basis. So the first property is that if I take a union over all possible open intervals, I get the full set. All possible open intervals cover the full real line. So that's one property. The second is that if I intersect two open intervals, A1, B1 intersection A2, B2, you can think about this. The result is either one open interval. If they are overlapping or one is contained in the other, then the intersection is one open interval. But if they are disjoint, then I have the union of two open intervals. So if this intersection is again a union, sorry, not if, this intersection is again a union of open intervals. This is just a fact. These are some facts that we are noticing about open intervals in R. Okay, so these are two properties. And the third is that, I'm sorry, I couldn't fit it on one page. Phi, the empty set, is an open interval. I mentioned this last time. What interval is it? It's the open interval A comma A for any A. Okay, it's the set of points which are greater than A and also less than A. So there are no such points. So that's phi. So three properties of open intervals in R. One, that the union covers the whole of R. Second, that the intersection of any two is the union of other open intervals. And the third is that the empty set is an open interval. Now we can, with this motivation, go to the abstract definition, which says that a basis, so a basis for a topological space S comma U is a preferred, by implication, it will be a smaller set of subsets of U with the property that Ui in the subset satisfy, and let's list it on the next page. One, that the union, I'm sorry, everything looks like U in this course, the union of all these Ui in the basis is equal to the full set. Two, the intersection of Ui with Uj, both being in the basis, is a union over some other UKs. And third, that phi is one of the Ui. So I hope you got my point. The key point here is that we don't always need to specify the entire collection, capital U, of open sets to specify a topology. It's enough to specify a basis, which are all in this collection, capital U, and then understand that all the other elements of capital U, which I didn't list, are nothing but unions of basis elements. So then U is all unions of basis sets. So we sort of reduce the problem of finding or listing all open sets to the problem of listing only the basis of open sets, and that's called a basis for the topology. So I hope that point is clear. We are now reaching 37 questions. So I think keeping the chat box closed was also a fun thing. Okay, so let's go to the, let's jump in and see how bad it can get. Arnab Goswami. Okay, that's new. All right, let's start from the top. Please explain the metric space again. Sorry, no, cannot do. I've explained it once and it's in the book and it will be in the recording. When defining an open disk, is this something for two-dimensional Euclidean space or the real line? Neither. The concept of open disk is for an abstract set. which has a metric defined on it. It's just called an open disk because we are doing the abstract version of some things that we already know. We are trying to go from concrete examples to abstract. So even though it's called an open disk, it doesn't look like a disk. It doesn't look open. It's just a mathematical name. And it's defined by the metric. All the points which in the given metric are closer than my starting point is an open disk. Okay. Topology of the space described above was the set of all open disks, right? I don't, no. The topology is not the set of all open disks because union of two open disks need not be an open disk. Let's give you an example. It's a good question in a way, and it's an exercise for later. Consider two-dimensional Euclidean space, the plane, okay? Now, in this Euclidean space, I can have this as my open disk, and here's another open disk, okay? Now, the union of these two is this. Is this a disk at all? It's not. It just doesn't look like a disk. It's not defined as the set of points which is closer than some value to some central point. It's not a disk. So, again, open disks are a way to define a topological space. They are not themselves the topology, okay? So the topology is not just the set of open disks. It never is, okay? How do we use metric in defining topology? What are the benefits of it? It's explained in the notes. Please take a look. By metric topology, do we mean the collection of all open sets defined using that metric? Yes, but it's tricky to define open sets using that metric. You have to do it in stages, and I've done the stages here. The stages are that I first define open disk, which you see here, and then I define open set by saying that the set is open if every time there's a point in the set, that point fits inside a disk, open disk, which fits fully inside the set. Now let's apply that to this example. Let's ask the question, supposing we take this example, but let's say I don't consider the union, I consider the intersection of two open disks. Okay, so here's an open disk, here's another. So the intersection of two should also be an open set. That's this, right? This is also not a disk, it's an open set. However, how do we know it's an open set? Because if I pick a point, let's pick a red point inside. Here's the point that I want to pick. Okay, then I can make an open disk which encloses that point and which is fully inside the set. Therefore, this weird shaped set is an open set, even though it's not an open disk. So you must be careful with notation. Open set is always the thing in a metric topology where the open disk around a point for sufficiently small open disk fits fully inside. Okay, that's the key point. Yeah. So metric topology is the collection of all open sets defined by this inclusion process. Yeah, axiom where we say collection of finite intersection and infinite union, opposite manner. Yes. Actually, Shanam, your question is we can actually define as closed in terms of closed sets. That's something maybe in the book. You can define a topological space in terms of closed sets. And in that case, it turns out that arbitrary intersection, but only finite unions are again closed sets. It's just a little sophistication, no point going into it here. Yeah. Shashwat, thank you. The exercise d of xy is x minus y whole squared won't be a metric as it won't satisfy triangle inequality. That's absolutely correct. Thank you. Are we using only R to define metric space? No, we are not using R to define metric space. I'll ask you to go back to the last lecture. I had a very important section in the beginning called Motivation to Definition. And I'd like all of you who are not clear about this point to write this on a piece of paper and paste it above the room where you study, wherever it may be, and ask yourself that at any given time, am I talking motivation or am I talking definition? Okay. If you ask yourself that question, you won't need to ask it to me. R and R2 are used as motivations and examples. the definitions are more general. They apply to R and R2 and Rn. They also apply to all topological spaces, much more general. We're not using anything to define a metric space. A metric space can be defined on 3 objects called red, blue, and green. Okay, or on 17 objects, any number of objects, infinitely many objects. It's just the axioms that I gave. Yeah. Okay. No notion of triangle equality. I don't know where complex numbers come in. Complex numbers from this point, you see, you're talking of again different categories. It's like, I don't know how to give an example. Complex numbers, no point. Okay. What are the conditions a topological space requires so that it can be endowed with a metric? So you weren't listening carefully, Harshad. I said that you can define a metric on any set, not necessarily a topological space. On any set, you can define a metric. You can define many metrics. It's up to you to find the metric. I've even given you a metric which can be defined on every set. D of xy is 0 if x is equal to y and 1 otherwise. No conditions need to be satisfied to be allowed to define a metric. Okay. The only thing is the metric, to be a valid metric, it needs to satisfy 3 conditions. Okay. The set doesn't need to satisfy any conditions, doesn't even need to be a topological space. Once we define the metric on the set, however, we can use the metric to make that space a topological space by defining the metric topology. Does the trivial topology contain 3 elements, 1, phi, and 2, s? I have no idea what this means. Phi and s are the 2 elements. I don't know what 1, phi, and 2, s means. Sorry. How can we fit open disks in the d equals 0 or 1 example? You need to try it, no? Have you tried it? Please try it. It's an exercise for you. By defining metric, we get open sets in that metric space. Now we see that these open sets satisfy axioms. Oh, now I understand Arnab Goswami. I'm really sorry. It's a real person. Sorry, excuse me. I got confused in between. Yeah. Yes, but Arnab, by defining a metric, we get some open sets, not all open sets. By defining a metric, first we get some, which are the disks, and through that we get all. Eventually we get all, that I agree. And then we see that these open sets satisfy the axioms of topology. That's an exercise to prove. Yes. Given a topology, is it possible to find a metric that gives the same open sets, Arjo? This is a good question. I don't know, but I would think it might not. Actually, very good question. I really don't know.
Yes, sir. Yeah. Actually, there is an Urshon metrization theorem, and it characterizes topological space which can be endowed with a metric.
Okay, good. Thank you. So yeah, okay. So maybe it's not always possible. Fine. In any metric space S, is all open sphere will be open set. Yes, those are that we call them open disks. We use disk even if the space is Euclidean or it's some other space. So yeah, in any metric space, all open disks will be open sets, and there'll be more. There'll be many more, which are formed by possible unions and intersections of these open disks. Weird metric is called the discrete metric. Yeah, I was saying if it had a name, probably it's called the discrete metric, and that almost gives away the topology that it defines. I'll leave the rest to you. Very good. If my set consists of lamp, table, and laptop, how do we define the operation dash? Why do we need dash? Sorry, I didn't run. Minus. I think you mean minus. Yeah. D of lamp and table. Well, I didn't define a metric. You can define a metric on lamp, table, and laptop, Agniva. Why don't you define it and tell us what metric you'd like to define? It is not lamp minus, there's nothing like lamp minus laptop, but there is something like D of lamp comma table. So you have to give me all the distances, D of lamp table, lamp laptop, table laptop, and we're done. Okay, there are 3 elements, so there are only 3 pairwise distances. You tell me the number, maybe 2, 7, and 45. Okay, and then check that it satisfies the triangle inequality. Probably what I've told you won't satisfy it. So you figure out the numbers. You can define any metric you like as long as it satisfies the axioms. But please don't try to do minus. We don't add or subtract elements of an abstract set because it's not a vector space. Again, I hope you're getting the point that everything we discuss doesn't have all the properties that you were brought up with in your childhood. That's the sort of beauty of maths. Okay. Every metric space is topological space, but not conversely. Yes, Arnab, you're right. But I would rather say it this way. Every metric space can be made a topological space using the metric topology. I could take a metric space and use some other topology if I felt like. Yeah. Good. Okay. I think I'm more or less, yeah, people have figured out that the discrete metric gives discrete topology. Thank you. Abstract basis, I think I explained it a few times. Can we define a metric on ordered triplets? So yeah, please resist this impulse to generalize things. That is not part of our discussion. In general, no, there's no concept of a metric on three objects. Finite intersection of open intervals can be written as union. Oh, yes, that's correct. That is Dhruv telling somebody. Okay. Basis, abstraction of open intervals. Pages were changed a little fast. Sorry, I have much more to do now. Why is the intersection of two disjoint open intervals not null set? It is a null set. Disjoint open intervals. Intersection is a null. Oh, sorry. I may have said something wrong. I may have said something wrong. The intersection of two open intervals, yeah, if they are disjoint, then the intersection is the null set. I think I said something wrong. Thank you, Rajnil, for correcting me. In principle, we can always define a metric on S. So can we define a metric on Minkowski space? Yeah. Okay. Good. Equivalence relations. I haven't said anything about equivalence relations. Open disk we define can be done via any metric. Achal, that is Achal Vinod. Yes, that is correct. Is metric topology defined with the parameter A, which was the parameter A is an arbitrary real number. So the metric topology, the metric is not defined with A, and topology is also not defined with A. A is not a property of the topology. The statement is that if X is inside a set, then X should be enclosable in an open disk of size A for some A. There should be some A such that there is an open disk which fits inside X. Then that capital X will be called an open set. Yes. Yeah. Good. Of course, many people have already gone to to more complicated examples. I think I'm almost through the questions. Can we go the other way around, going from a topological space to a metric space? I don't think that's very natural. It so happens that R is a topological space and a metric space. In general, metric is a simpler concept. Metric is just some set of numbers assigned to every pair of points. That's really all it is. But which satisfies triangle inequality. The other conditions are quite trivial. Yeah. Amit, I cannot give an example like writing ds squared because I'm not working in real. Ds squared is a construction of Euclidean space or of a differentiable manifold, and differentiable manifolds are many lectures away. Please be patient. Good. Okay. Indiscrete topology doesn't have a metric for it. Yeah, I think it doesn't, but maybe it does. I don't know. Maybe I don't know. It probably doesn't. Good. Thank you all. Chat box off. Let's go on. I'm wondering if my Apple Pencil is charged. If you give me a second, I will actually check that. So let's see. I'm really sorry. My Apple Pencil is fully charged. What do you know? Okay, so now I can go to a better app where I'm a little more comfortable and write a little more neatly for you. Good. Okay, but I don't think you can see it anymore, because I think sharing my screen stopped at some point. Share screen, yes. Good. So let's continue. Okay, lots more to do. So now we are going to turn to a new concept called closure. I bet you're happy that my handwriting is a bit nicer. So recall Again, we keep doing this. Recall in R, again, motivation, alert, that we had open intervals and we had closed intervals. And the only difference was that this was A less than X less than B, and this was A less than or equal to X less than or equal B. And these were open and these were closed. So this gives us a kind of thought which may come to us. Can we close an open set by adding its endpoints? Okay, the things I've put in quotes are things which are not at the moment well defined. It's just an intuitive question. In R, it's well defined. We can certainly add the endpoints of an open interval and make it a closed interval. That's just a fact in the definition. But is it more general? Now, see what the obstacle is to going more general. In general, we don't necessarily have a metric. We don't necessarily have any concept of limit or endpoint. So no concept of end point. Okay. And in fact, there's a beautiful idea, concept, which we can introduce in a general topological space, which will enable us to define something called like an endpoint, which will be such points that if we add them to an open set, it will become closed. This establishes a nice relationship between open and closed sets. Right now, the only relationship was that the complement of open sets is closed and vice versa. But now we are actually trying to take an open set and understand if there's some way we can fidget with it to make it closed. Okay, so we are going to define the concept of a limit point. Now, confusion alert, this limit point will be defined in an arbitrary topological space, not in R or R2 or complex numbers, for goodness sake. Arbitrary. So they don't look limit like. There's no concept of limit in a topological space because there are no continuous variable necessarily, and I can't do epsilon and delta in calculus. That's exactly what we're trying to drop when we do topology. Okay, but we still have a concept of limit point, and you have to understand that the only meaning is the meaning I'm going to give now, the definition of limit point for an arbitrary space. But this will, of course, describe what we otherwise understand as limit point in Euclidean space, but it will be more general. Okay, so the setting is I have S and U, a topological space, and I take a set A in S. Right now, I'm not going to say whether this set capital A is an open set or not, or closed or any other. Just it's any subset of my full set. Okay, now I'll say that a point small s in A is called a limit point of A if whenever S is in some open set U in U. I'll explain this. The following condition is true, that U minus this point has a non-trivial intersection with A. Okay. So this perhaps is the first moment this course got a little bit difficult. If you didn't get it in one breath, give me some time to explain it. So the idea is the following. I have a set, I have a big set. Well, let me try to do it pictorially. I have a big set S. You shouldn't think of this as a space. It's just a set of points. and some A in it. Okay. Now, basically what I'm going to do is consider any, I might have said something wrong already. Even I get confused. I don't know why I said even I get confused. I always get confused. It's not a point in A, sorry. Any point in the full set is, yeah. Let's just review this. A point small s in the set is called a limit point of A if whenever S is in an open set, then that open set minus S has a non-trivial intersection with the set A. So you can think of it like this. Here's the set S. Let me now try to look at a point S, small s, which is in my space capital S. And let me take, again, this is very schematic, but let me just take it anywhere, small s. Okay. Now, I'd like to call it a limit point of A if the following is true, that whenever I put an open set around S, that is, I have an open set in which S lies, that open set always intersects with A. Okay, this is the key point. Now, this point S need not have been in A. Of course, if the point S is in A, and if A is an open set, then obviously I can enclose S in an open set, which is in A by definition of open set. But never did I say that A is an open set. Okay, A can be any kind of set, and S can be any point in the big set. Okay, but the concept of limit point is that S is in some sense in my topology so close to the set A that any open set which I put around S is going to spill over into A. It's going to intersect with A. Okay, so that's the concept of limit point, but I emphasize limit point can be defined on the topological space of lamp, table, and laptop with the topology that we defined last time. And there is a concept of limit point. It might be a little trivial, but it's very well defined because it's defined entirely in terms of a set, its subsets, and its open sets. Okay. So let's look at some more familiar examples. The familiar examples are always in Euclidean space. So let's consider this, which is an actual open disk in R2. Okay, so this is the unit circle, let's say, and I consider A to be this set. So A is the set of all x such that mod x is less than 1. Okay, so it's the unit circle and everything inside it. Now, let me take my point S here. S is itself a point whose position vector is mod is less than 1. Now, the question is, now let me take any open set in which S lies. Okay, and let me remove S, only the rest of that open set. Now, does the rest of that open set intersect with A? Yes, in fact, it can lie fully in A, it can lie partly outside A, but it certainly intersects with A, right? I can never find an open set which contains S and which doesn't intersect with A. Okay, so every point, so every element of A is already a limit point of A. And it's not very interesting because we are not looking for limit points which are already in the set. What about elements which are not in A? Yes, not in A. Okay, so let's go back to this A and let's draw it again. This is my A. And now I'll take an S here. Remember, S has to be in my big set, capital S, which in this case is the plane. So I'm entitled to take it outside. Now, is this a limit point of A? Okay, for it to be a limit point, every open set which contains S should have an overlap with A. But clearly from my drawing, I can find an open set U which contains S. And when I remove S, the rest of it doesn't have any intersection with A. Okay, so in this case, S with mod X greater than 1 is not a limit point of A. So this worked fine. the points inside the disk are limit points, the points outside are not limit points. There was no work required for that. What about points on the boundary? Now comes the fun. If I have a point here, and this is my S is not in A. So this point is on the boundary, but remember, this is the disk with mod x less than 1, not less than or equal to 1. So in this case, I chose A wisely to be an open disk. And now S is not in A. But is it a limit point of A? And you probably guessed it. Even though it's not in A, yes, it is a limit point of A. Why? Because take any open set that includes S. Okay? Now, any, however small. Now remove S. Okay? The rest of it, does it have an overlap with A? And yes, it does. Okay? There is no way to get an open set which includes S and doesn't overlap with A. Yeah. Why do we remove? Sorry, I couldn't help it. It popped up and it's a natural question. Because we are not interested in that question about whether S belongs to A or not. We are interested in the limiting nature, which means that not just S, but points which surround it in the sense of open sets, in the topology, not in the metric, not in terms of distance, but in the sense of open sets which contain it. Do those necessarily spill over into the set A? Okay, so this is the precise definition. It's very precise. You can't tamper with it. It's not correct if I don't remove S. You can take some time to think over that. It'll also follow from some of the exercises. Okay, so I hope you grasp. So therefore, all points with mod x equals 1 are limit points of the open disk A. Got it? Okay. So this is a key result. And as I said, these points don't belong to A, but they are limit points of A. This is the very important fact. Okay. And in this sense, we now see that in the example, the limit points which are interesting are points which are not in A, but they're still limit points. Okay. So I could consider taking A and adding to it its limit points. And that's a very logical definition. Take any set. Now back to a generic, that was the example. Example is over. Take any set A in S. There's assumed to be a topology. Subset of S. And add all its limit points. Add all its limit points, then we get what is called the closure of A. We have taken an open thing and added some specially chosen points and called this a closure. And well, there's a theorem. So therefore, closure of A, which is denoted A bar. This is something that often occurs, by the way, in physics. So it's worth keeping in mind. So A bar is the set A union all limit points of A, regardless whether they were in A or not. If they were in A, it doesn't matter. You can add them. You don't have to add them because it's a union. But if they were not in A, you have to now add them. And so A, this is the closure of A. Now I've used a suggestive word, but there's a theorem now that if I do exactly what I said, then A bar is always a closed set in the topology. So this answers the question I had. How do we take a set that's in some sense that's not closed, that's either open or somewhat open, not really an open set even. What can we do with any set and make it closed? By the way, A bar is defined regardless whether the original A was an open set or a closed set or neither. Okay. I can take any set and add its limit points. But to add its limit points, I need to have a topology, because limit points are defined through open sets of the topology. Otherwise, there's no definition of limit points. And they're not defined through a metric. In the metric topology, they'll be defined through a metric, but I'm not assuming a metric topology now. So in a way, the open sets are helping me to define the concept of neighborhood even where distance is not specified. Very important to understand that open sets is a more primitive, therefore more general sense of what is in the neighborhood than a metric or a concept of distance. Good. This theorem needs proof, and you are going to prove it. All 383 of you are going to sit after this and prove it for yourselves. It requires nothing more than all the axioms, all the definitions. Let's just say all the definitions. So let's run through that. Take a set A and add to it all its limit points as per the definition that I gave of limit points. Namely, whenever S is enclosed in an open set, then that open set minus S has a non-trivial intersection with A. All right. Now I take the union of A with those limit points. Now what should I do to prove that A bar is closed? I should look at its complement and prove that the complement is open. Closed set has one and only one meaning in topology. It's the complement of an open set. Okay. Again, from your intuition, you may have thought it's something else, and it is many other things, partly because of theorems like this. But the definition in topology is it's the complement of an open set. So take A bar defined as A union its limit points. Now take A bar prime. So proof, so I'm not giving the proof, I'm just writing what to do. Take A bar prime, complement of the closure of A, and prove that it's an open set in the topology. That's it. It's quite doable, and you'll see that it's very beautiful because it's sort of quite complementary in a way. It's like closed and open already have certain complementary nature, and this theorem actually in some sense highlights that complementarity very nicely. You can take any set, you can make it closed by adding limit points, and that means its complement will be open. Okay, good. Okay, and one more definition, then I'll again look at questions, and then I have another 10 minutes or so, 10 or 15 minutes, then again we can take questions. So one thing which is just a very simple, I could have given it to you much earlier, but this is an appropriate point to give you the definition. Definition of relative topology. So supposing I'm given a topology, which is a set S and a collection of its open sets, and a subset A, which is a subset of S, okay, then now I want to define a topology on A. Now A will be my S, okay, so it's a relative topology on a subset of the full set. So A will be my subset. In physics, you can think, if S was a manifold, A might be a submanifold, something like that. But we haven't defined manifolds yet, and this is not only for manifolds, it's for general topological spaces. So we'll define a topology on A in the following way. So we'll say that we'll call that topology A and capital U sub A. Capital U sub A is the open set of open sets on A. And we'll say that UA is the set of UI intersection A, where the UI are in the original collection U. Namely, take, so this is meant to be subscript. Take the original topology, it has a bunch of open sets. Each one of them, one by one, I intersect with A. Okay, because I'm trying to define a topology on A, and if my open set UI has some part that's not in A, it's not going to help me because my new relative topology is supposed to be on the smaller subset A. Okay, I'll show it to you pictorially. So the claim is that this definition of UA is again a topology. Okay, so that's it. Let's look at an example. Not example, let's look at a picture. So here is my full set S, and let's say it has all these open sets. It's just meant to be very pictorial. These are various open sets. Now let A be a set like this. Okay, it's a smaller set. So this is A, while the other one was S. These blue circles are the open sets of S. Now what I'm going to say is that here are the open sets of A. Just take those and keep whatever's inside A. If that open set of S was fully inside A to start with, that's fine. Keep it all. Because in that case, UI intersection A is UI again. If it's partly intersecting with A, only keep that part. Okay. So this defines a topology on A, starting with a topology on S, which was a bigger set. So this is called the relative topology. And one small comment, sets which are open, which my spelling is going to help. Yeah, sets which are open in A need not be open in S. Look at it this way. These circular things were meant to be open sets in S, this kind of thing. Okay, but nobody said that this weirdly shaped set is an open set in S. It's merely the intersection of an open set of S with the whole space A. Okay, so if I refer this intersection back to S, it may not be one of the open sets in S in general. Okay, but it's an open set in A. You can have some fun with this if you want an interesting example, which is not in the book actually. Supposing my S was the whole plane and my A was just the right half plane with a boundary here. And suppose it included this boundary. Okay, then open sets of S, as we know, can be provided by a basis of disks. So I can have open disks and all the intersections. Well, now the relative topology on the right half plane is open disks which are fully inside A, but also disks like this, which are not disks anymore. They are intersections of disks with the right half plane. And these ones actually contain this boundary, this vertical part. Okay, so they are not open in S, but they are open in A in the relative topology. Okay, so this is a subtlety you need to keep in mind. Very good. Okay, I read this, but let's go quickly through the questions. Actually, I enjoy the questions. It really helps me learn how people are following. Please disable the chat box. You can close your chat box. Rupayan, I was doing that. You can open it whenever you like. Chats is open, yes. Yeah, I might have said something wrong from time to time. If you want to point that out, you need to point it out a little bit more carefully. Can we use open disks without using them? Yeah, okay. So this is important. Rukmini has asked, what if for S outside A, I can take whatever U I want, which will have S and intersect with A. So remember, it's a limit point if every U intersects with A. And one thing it's a good thing, I'm glad you asked it. It's not any U intersects with A, but every. You must be very alert in a mathematics lecture or even mathematics for physicists to the difference between any and every, all, some, or, and. These are very, very important. So in this definition, S is a limit point if every open set that surrounds S intersects with A. Okay, this is very important. Okay. Yeah, Abhinav has tried to explain why we remove S. Okay. Is there a way to tell that we have found all the limit points? I didn't give any construction, Maitreyi. Thanks for the question, but I didn't give any construction. These are all in principle. Actually, there's no way to, in general, to check anything I've said. Okay, you have to have a definite topology, and then you have to be clever to find ways to check things. But certainly, there is a sense in which you can write all the limit points in principle and add them to the set. Yeah. Okay. How we defined open sets without using open disk? Yes, Aridip. The answer is the original definition was I just tell you all the open sets. I start with a set S. I tell you all the points in it. Okay. Now, of course, anyone that list contains phi and s, that its unions are back in the list, that its finite intersections are back in the list. If all that is true, I've defined open sets. I don't need any disks, and I don't need any metric, and I don't need any basis. That's the original definition of topological space from last time. Yeah. Yeah, Achal, Vinod, yes. In some sense, we are deriving a topology from the bigger, lack of better word, topology. Actually, yes, I mean, you can say there is a better word. We are defining topology on a subset in terms of topology on a bigger set, which contains my subset, which is contained by my, sorry, which contains my subset. I said it right first time. Yeah. Yeah. Good. Can we have limit points of a closed set that are not in that closed set? No, actually, a closed set contains all its limit points. So that's the point is that follows from a theorem which I asked you to prove. If you look at it carefully, the fact that the closure is closed, you can use that to also prove that a closed set already contains all its limit points. There aren't any missing. If it's a complement of an open set, it will have all its limit points. That's a provable theorem. Yeah, good, good, good. Okay, very good. Open disk is same as open ball, Avinash. I wouldn't say so. In your mind, open ball is well, in my mind, open ball is a concept on Euclidean space only. I'm using open disk because I chose that word for an abstract topological space. I could have called it open ball, but I didn't. I called it open disk. So open ball is something that we use generally for arbitrary Euclidean space of dimension n, then it's an n-dimensional sphere. Okay, but if you're not doing Euclidean space, we're doing the abstract case, we just call it open disk, no matter what it looks like. It could look like a 100-dimensional space, or it could look nothing like Euclidean space. It's always called an open disk. It's the set of all points closer than a given distance to the specified point in the metric, in that metric topology. So it's only defined in a metric topology. That's the important thing. Open disk is always defined with respect to a metric. Great. Okay. Yes. The new relative topology is not S and A. I think I showed you what the relative topology was. It is A and UA. Oh, oops! I lost my screen share again. Somebody should shout whenever that happens. I'm not sure what I do. I think it's my iPad going into sleep mode, which I shouldn't allow. Yeah. Good. So yeah, it's so the new relative topology, Suraj, is A is the set and UA are the open sets, and the UA are nothing but the small ui intersected with A. Okay. Good, good, good. Okay, so that was fine. Closing chat box again and take a few more minutes. We are making much better progress than last time is what I can say. And let's talk about connected and compact spaces. And then we can actually think of addressing our original question. This is a bit tough stuff. I don't know how far I want to go today. I'd much rather go slowly rather than rush through things. But connected, at least I think I can do today, and compact along with continuity, we may leave for the next time. And I'll revise the contents. Connected space. Now, connectedness is very important, right? Because in topology, when people talk about topology and they talk about deforming spaces like plasticine, like rubber, sheets of rubber and all that, obviously, when you break something in pieces, you have done something to change the topology. That's sort of what you should be getting from the for the social media level of definition of topology. Breaking is something which disconnects an object, okay? And so we need to know what is connected, but we are in a topological space, we're not in Euclidean space, and we don't have that Euclidean space notion of connected and disconnected. So what should we do? We need a definition. So using the motivation, we give the following definition. Topological space S and its collection of open sets is called connected. This is a definition. This is what it's called if it cannot be expressed as a union of disjoint open sets. In other words, alternatively, if it can be expressed as a union of disjoint open sets, then we call it disconnected. Okay, so let's give the example of, let's give a more precise definition of disconnected, then we'll see that connected is the opposite of that. Disconnected is that there exist U1 and U2 in the topology U, the collection of open sets, such that U1 intersection U2 is null, but U1 union U2 is the full set S. Okay, so I have two open sets. Their union is the full set, but they have no points in common. Okay, then we call the space disconnected. If that's not possible to do at all, then the space is connected. And as soon as we look at a couple of examples, this thing will start to make a little more sense. And there's a nice theorem which I shouldn't forget. First, let me state the theorem, and then let me look at examples. In a connected topological space, the only, I forgot to say something. I even forgot it in the book. I'll just come to it. Only sets that are both open and closed are phi and S, the full space and the null set. So I forgot to say something. If one of you was looking very sharp at my definitions, you would say, well, let me take any topological space S and U. Let me take U1 to be phi and U2 to be S. Then, of course, U1 intersection U2 is phi and U1 union U2 is S. So every space is disconnected. That's obviously wrong. So I should say disjoint proper. And here for the first time, I'm talking of proper open sets. By proper, I mean which are not phi and S. Okay, they are open sets which are proper subsets of S. All right, let's look at the example, and then we'll basically stop for the day. And yeah, so let's look at R, the real line. Again, some of you are sick of me saying this. This is the example. It's not the general story, but we want to see that the definition reduces to things we already know, and it's more general. It applies in any topological space, because as you see from the definition, it just is a property of the open sets of that space. It has nothing again to do with Euclidean or metric or any other thing. Okay, good. Now let's look at R. Is it connected or disconnected? Okay. So can I find two open sets of R which have no points in common and whose union is R? So let me try. I'll take one open set to be the one from 0 to infinity and the other to be from 0 to minus infinity. Okay, so U1 is this and U2 is this. Okay, now U1 intersection U2 is certainly phi. They have no points in common. neither of them contains 0. Okay, and that was the only point where they were anywhere close. Otherwise, any point less than 0 is in U1, not in U2, and other way around. Okay, now what about U1 union U2? Well, this is almost R, but it's missing the origin. So it's R minus the origin. Okay, so it's not R. Okay, so I haven't been able to partition R into a union of disjoint open sets. However, this tells me that R minus the point 0, which I just delete. Now it's good. So this is R minus 0. So this one is connected. This one looks disconnected in my intuition because this point is missing. Right? And it is actually the union of minus infinity 0, which is an open set, union 0 plus infinity. So it's disconnected. So this is good because the real line minus a point in front of my eyes has fallen apart into two parts. So it's disconnected. Okay. There's no continuous way to get from one to the other because there's a point that's just not there. And the topology definition works because this disconnected space can be written as union of disjoint open sets, but the connected one cannot. I only tried once, but you can keep trying other ways to cover R with disjoint open sets. If you try by taking your first open set to start to end here, and the second to start here, now you're covering R, but they're no longer disjoint. You see, that's why there are two requirements, this one and this one. They should be disjoint and their union should be the full set. Yeah. Okay. Good. So this is the concept of a connected space. And this is a theorem that I wrote, which is that in a connected topological space, the only sets that are both open and closed are the empty set and the full set. That's anyway obvious. They are open and closed right from the beginning. We noted that there aren't any other. So at least in a connected space, the concept of being open or closed is mutually exclusive. Okay, that at least gives us some reassurance that in a connected space there is some sense in which open sets are special. In a disconnected space, of course, what happens is that then the space can be thought of as breaking into two components, and you can work with each component separately. So in physics, we often talk of connected component of the Lorentz group or something, and those components will be together forming a disconnected space, but each one will be connected. Good. Okay, now before I take questions, one last comment. Connectedness definitely depends on the topology, because I said that it is found out by looking at open sets. So for example, if I look at the discrete topology in which everybody is an open set, you can see right away what's going to go wrong. In the discrete topology, every element of S is an open set. Okay. So if I take the union of all S over all S in capital S, this is equal to S. And obviously every element is disjoint from every other. So S, the full set, is disconnected, is always disconnected. Even the real line is disconnected in the discrete topology. Okay, and it's the other way around for the indiscrete topology. Everything is connected because essentially there are no open sets. So there's no way I can even check that theorem. I don't know if that's a meaningful statement, but certainly in the discrete topology, any set, even the real line or real Euclidean space, can be thought of as or becomes by this definition disconnected because it can be written as the union of open sets which are all mutually disjoint. So that's important because now we have made sort of a first step towards the idea of understanding what continuity means, even though I never use the word continuity and it will only come next time, because connectedness is an allied concept. It's an independent concept by all means, but it has some connection to our intuition about topology, what topology is. And yeah, so that's why connectedness is an important thing. Okay, last round of questions. To prove, yeah, yes. Dhruv, absolutely. To prove connectedness, we need to show that every pair of open sets fails to satisfy connectedness. That's correct. I think I said it eventually. Um, um, no, I didn't understand. Yeah. Is it possible to define a metric or distance using concept of limit points? No, I don't think so. So in R, we'll have 1, 3 as disconnected 1, 2, and 2, 3. No, it's 1, 3 is not the union of 1, 2, and 2, 3 because the point 2 is missing. If by these brackets you mean open intervals, the point 2 is not in 1, 2 and it's not in 2, 3, but it is in 1, 3. So be careful about that. Yeah, it doesn't contain. People have pointed that out. Thank you. Okay. Infinity won't be included. Sorry, that question is infinity won't be included in what? Yeah, I didn't understand the context. You'll have to write your question a little more in a self-contained way. Yes, we do not need a metric to define connectedness. Yes, correct. That is correct, Nikhil. Have we discussed disjoint open sets prior to this, or did you miss something? Yes, you missed the first sentence of my course when I said that we are supposed to know what intersection and union means. And one of the important things in intersection is that when A intersection B is empty set, then we call those two sets disjoint. Disjoint means precisely that the intersection is phi. I defined it again. Since there are uncountable open sets in R, we cannot show connectedness of R by manually picking pairs of open sets. Absolutely true. But we can still show it. Okay, it's only we can't do it by listing the pairs of open sets. But what we can do is simply always go back to the definition. Okay, I wasn't trying to give you a proof. And Dhruv, I think you're probably looking in too many places for proofs in my course. Where a proof is needed, I've tried to say it in the book. Even there, I haven't always said it. Okay, but this is exactly the difference between what I'm doing and what Singer and Thorpe did in their book, which I've listed and which I hope you have looked at. Singer and Thorpe exactly does the opposite of what I'm doing. Instead of going into examples, it goes into theorems and proves the theorem. The theorem proofs are there. Okay, so how will we prove that R is connected in the usual topology as a theorem? I'm not giving you the proof right now, but I'll tell you what you have to do. You have to say, assume a set of open sets, which are all disjoint and which are all, the union is R. Okay, first let's assume. That's called assuming the contrary. Now use the definition of open set, namely that if a point is in any of the open sets, it can be enclosed in an open interval which is also in that set, and show that there's a contradiction. So that all has to be done. And I'm not at all implying that I'm doing it here. So please, if you think that by me showing you that R is not connected, R is connected by showing two open sets and the fact that they don't satisfy that, if you thought that was meant to be a proof, that's not the style and that's not the plan. And this will be a problem in future. So I would advise that you get used to it. Yeah. There's another definition of being connected, like only a null and whole set being both open and closed. The one you provided has some sort of geometrical connotation. No Ajas, no geometrical connotation, only topological. The one which discusses being open and closed also is topological. No geometry anywhere at all whatsoever. Only topological. The definition of connectedness was given entirely in terms of union and intersection of open sets. And the open sets are the ones in that topology. Nothing more and nothing less. No geometry. Okay. So in fact, they are equivalent. And I just quoted for you. Now my iPad has slept. I'll change that setting later. I quoted for you a theorem, and that theorem actually works in both directions. So let's see it. In a connected topological space, the only sets that are both open and closed are phi and s. Okay, so that is as per my definition of connected. Okay, the converse is also true. If the only sets that are both open and closed are phi and s, then this property also holds. Okay, so I can define connected space by saying the only sets that are both open and closed are phi and s. And then I can prove the theorem that in a connected space, you can't have a disjoint union which span of open sets spanning the space. Okay, I hope that's clear. Yeah. R minus 0 won't be a topological space because the identity isn't there. Yeah, there's no concept of identity. So, your identity is a concept in group theory. Okay. It's a concept in multiplication. Nothing that there's nothing like product of lamp and laptop. Okay. They're only open sets. There's nothing else. It's very difficult when attempting to get some mathematical intuition to shed the things we know. Okay, but I'll certainly advise you to try and shed all the things before you learn this, if this is something you want to learn at the given level at which I'm teaching it. If on the other hand you want to do the rigorous thing, Singer and Thorpe is the book, and believe me, I spent several months of my life reading it end to end, and it was one of the greatest times of my life. I didn't master it, but I enjoyed it. It's a wonderful book. So please look for your proofs there, and please keep in mind that don't bring in concepts like identity or negative or subtraction or addition in a topological space. In fact, ask yourself whenever you name a concept, is it defined in a topology? Is it part of the definition of topological space? If not, can't use it. Yeah. Good. Ogniva, yes. Can 0 be considered a limit point of R minus 0? Yes, it is a limit point. That's correct. Now, here, the discussion of R minus 0 was in the context of being disconnected, but it's also true that R minus 0, being a union of two open sets, is open, right? And it's not closed. Now, if I add 0, now it's closed, and it's no longer, so now it's just closed, yeah. So yes, 0, it's not can be considered. 0 is a limit point of R minus 0 usual topology. But I don't think this means that we can make a space connected by adding its limit points. After all, I can show you a disconnected space which just, which are just two separate intervals, not separated by a point. I can have R minus a unit interval, okay? Now I can't make it connected by adding its limit point. So connectedness and closure are two different things. There's some relation, but not that much. Is connectedness local or global feature of topological space? There's no such thing as local in a topological space. Local is geometry. There's no geometry. There's no local. There's no metric. There's no where are we in a topological space. Okay. So please don't, continuous function will wait. It's one more lecture for that. Yes. Sanjana is quite right. For every pair of open sets whose union is R, the intersection is non-empty. That's probably the smartest way to prove it. I agree. Yes. Now, as far as inclusion brackets, sorry, I again lost this. There's a comment that I shouldn't have put inclusion brackets for infinity. I don't know if that matters. Maybe that's, I guess that's, I'm not sure. Maybe that's the convention. Yeah, I shouldn't do it. You're right. You're right. It doesn't matter. Infinity is not there. So yeah, probably I shouldn't do it. I'm desperately trying to reconnect, but I think we are also out of time. I really apologize for losing the screen share. I will fix that from next time, and I'll also charge my Apple Pencil. It's really so annoying. Yeah. So thank you. Oops.
It's working now.
Yeah. Corrected. Okay. Why in example of relative topology, the point on y-axis was included in right half plane? Suraj, because I chose the subset to be the right half plane, including the boundary. and define the relative topology on it. I could also choose the subset A to not include the boundary, then I would define a relative topology on that. I can define relative topology on any subset. Purposely, I chose it to be not an open set. See, the right half plane with the boundary included is not an open set in the plane. I chose it that way to show you that the open sets in the relative topology need not be open sets in the original topology. But if I had chosen the subset A to be open, then by the axioms, it's immediate that open sets of the relative topology are open sets of the bigger topology. Yeah. Yeah, Himanshu, please do stop dreaming about geometry. The rate at which this course is going, we'll never reach it. So please wait till we introduce geometry. Topology is not geometry. Repeat, topology is not geometry. It's not vector. It's not algebra. And it's not, what other thing? Group theory. It's not anything except topology, actually. Yeah. Good. Thank you all. Recordings are available. Sudipto, please.
Yeah, so I'm trying very hard to edit them on time. So
Yeah.
hopefully we'll be able to give you the recording of both the courses. So what I'll do is that I'll edit it, upload in the YouTube and share the link. I don't want to share the unedited video.
No, thank you. I agree. You can spare me lots of embarrassment by doing that. Are you editing out even my mistakes and all? That would be too much work.
Okay.
That you need not
I
do.
hope so.
That you need not do. Sorry, Aditya Milind Kolhatkar. What are the mathematical prerequisites for trying to read Singer and Thorpe? Honestly, the same as for this course, but it's at a real level. It's for mathematicians, so it's at a different level of sophistication, and you'll have to follow details. So you can read it from page 1 if you read every single line and work out everything. The speed, I would say, would be a tenth of or a fifth of, at least at best, a fifth of what I'm doing. Yeah. Thank you all. Thank you all. You've been a wonderful audience. See you next time with a better configured iPad and Apple Pencil. Bye.